Hey there, welcome to another problem session. Today we have a very interesting problem. You can see that we've been doing satellite and comets and planetary motions. So today is a satellite around Earth, and in this video is being made in 2022. So there's a lot of talk about how many satellites Elon Musk is going to put in the orbit. And so here is one of the satellites. It's called this. I looked up on internet. It's perigee height and apogee height. What they are is, if it was sun, we'll call it perihelion, but when it's Earth, it's called perigee, nearest point. And this is a height, which means height above Earth. Okay, so it's if I just draw a picture of the orbit, and the Earth will be like that, and here is the center. And in a two-body problem with one more massive than the other, you can have center of mass and center of the big body being more or less the same place. So all the distance will be measured from here, and so what's given is this distance and this distance. So this is height apogee and this is height perigee. What goes into the calculations are these distances. So this distance will be RP, and from here to here that distance will be RA. And you may remember that in two-body problem, this is the solution for the satellite or a smaller body. And the way we have the coordinates is this is the distance R, and you go towards the aphelion, apogee, and this angle is theta. Okay, so that's the angle. And this is where the aphelion is, and this is where the perihelion is. This is where the apogee is. In case of Earth, we say it's apogee and this is perigee. Okay, so these are very actually HA and HP are very near to each other. So the orbit is almost circular, and we're supposed to find minimum energy required to place this satellite in this orbit. Okay, what's the minimum energy? What does the minimum mean? Minimum means when you shoot the satellite from Earth, there's a lot of energy that goes into friction and overcoming the drag, and we're supposed to ignore that, and that's what gives you the minimum. Ignoring minimum means ignore a loss of energy due to drag and friction. Okay, so the problem becomes, if you look at it, if I'm here and I shoot whatever direction I shoot, and initially, so this is like V equal to 0 before launch. So the energy is 0, energy of satellite, and it's going, say it going in that direction. So at any point, it's going in that direction. So it's got some speed. It's VA here. When it's over here, is V is over here. Over here, I'm going to call it VP. So these speeds will change depending on where it is because the distance is different. And so let's see, energy here will be E. And this energy E is the same as here. Energy is also E. So it's same in wherever it is, but it's not equal to E0. This E is not equal to E0. And that's the difference that I have to provide. So E needed, so additional energy needed is equal to E minus E0. So we need to figure out that. Okay, that's what A is. So how do we figure out E? Well, from the previous part of this series of lectures and problem solving, you may know that energy is given in this is the kinetic energy, and this is the potential energy, and you can simplify it, and it will be this will be the energy, and A is same measure axis. This total is 2A. So A is, you can see, RP plus RA, and RP will be radius of the earth plus HP, radius of the earth plus HP, and RA will be radius of the earth plus HA. Alpha is this. So if you write down the energy like this, minus G mass of the earth, mass of the satellite, over 2 times RP plus RA, and don't forget RP has these things. What's given is these guys are given. RP and RA are not given. So over here I need to know mass of the earth, but it is also given to us that we can use this to replace some of that, and that turns out to be minus G RE square, so mg RE square 2 times RP plus RA. So that's the energy. Okay, now we have everything here, and I can put the numbers, and I will kind of pause the video and go out and do the calculation and give you the numerical value. Okay, so I found the answer here. I went and did all the calculation. I like to do the calculation, just a little secret here I want to share, that how I do this kind of complicated calculations is I use like a Python script, and I just put all the values, and I forgot M, so I got an error here, but I put the M here, and then I can kind of scroll back there, and it's a hit, and this all gives me the number. It gave me 3.279, all this, and then I kind of read up the digits from here, and that's how I kind of do the calculation. And hopefully that does not have too many mistakes, but you never know when you're doing the numerical calculations. Always there's a chance of an error. Okay, so that's E, but we are really not looking for E. We're looking for E minus E0. So we need to get E0 also. So what's E0? To get E0, so here's the Earth, and satellite is sitting there at V equal to 0. And it is sitting at a distance radius of the Earth. So just going to have a gravitational potential energy. So E0 is just going to be, if you look at energy, is kinetic energy plus potential energy. And this R is radius of the Earth. So it's going to be minus G mass of the Earth, mass of the satellite, over radius of the Earth. And this one we already said we're going to do G RE square, and then this RE cancels this. So this is just minus mgre, and I can just find the answer doing the calculation, because I already have the script. I can just it just minus m times g times r, and gives me now we have a 3 plus 6 here, and 9, so 14.2. So this is equal to 14 minus 14.2 times 10 to the power 9 joules. I kept 9 here and 9 here so that I can, when I'm doing the calculation, next step I don't have to repeat it. So what I want, E minus E0, and this is minus 3.3, and everything times 10 to the power 9, and this will become, flip the sign and becomes 14.2, and so this is 0.9, and it's 10.9 times 10 to the power 9 joules. Might as well call it 11 times 10 to the power 9 joules. So that's the answer for A. Okay, let me clean this up and do B. Okay, so how do we do B? For B, we'll, let me get a different color pen. For B, we will need to use this energy. So we want to know how fast it's going, say Vp, and from the axis the distance is Rp, and Rp is this quantity. So if I look at this, it will have this much energy, but this energy is same as what we calculated at any point in the orbit. So energy at any point in the orbit is the same as energy over here, same. So we already know the answer to the energy, so this value, and I'm going to wait till the end to use that. So we get a formula: energy at any point in the orbit is equal to energy over here, energy when it's at the perihelion. So for the perihelion, you have a half Vp square minus alpha R perihelion, and alpha is, as you know, that's the answer over here. Okay, we want this, so of course we can just arrange that. So we just erase from here and solve this. E is already known, everything else is known, so you can see this on the other side. I get E plus alpha over Rp, and this gets 2 over m, and then get a square root, and that's the Vp. And I would be able to solve this using the same techniques I have done before. Okay, so just put the numbers in there. Let me get the alpha out. So the alpha is g, mass of the earth, m, and m is can cancel out here. So let's put m over here and m over here, and so alpha is going to be just with m cancels out, this will be just gm. And so kind of same things we're using. You have E over m plus gm was GRE square, E square over Rp. Let me, so we have this, and I am going to give you the numerical value when I work it out. Okay, so I put in these formulas over there, and I just use the Python script. and it is 9,000, so 9.3 kilometer per second. So this will be just it's going to come out to be 9.31 kilometer per second. So that's going to be answer for VP. So how about V at the aphelion over here? One way to do it is just kind of repeat this with RP replaced by RA, and you should get some answer here. Another way is, so one way is repeat BP calculation by replacing RP by RA. Another way is to use angular momentum conservation. So use angular momentum conservation. Okay, I'll leave this for you. Leave this for you to complete. Let me talk about extensions of this problem, kind of other kinds of problems that you can solve. Okay, clean it up. Okay, the final answer is this. I obtained by just kind of getting the E and then getting the E in the Python script and just typing the formula that's over here. Okay, so how do you get a VA? Well, you can get VA by repeating VP this calculation with RP by RA, or you can just use an angular momentum conservation. I'll just leave this for you, and let me pause this, and I'll go to extension of this problem that are interesting for you to solve. Okay, extensions. Let's look at extensions. So one thing you can solve is not just energy at any point, energy anywhere, but what is the angular momentum? Another interesting thing is the satellite is going, Earth is like that, and satellite is going around, so it has a period T of the satellite, and you can use Newton's equation derived formula, or you can use third law of Kepler. So these are a couple of extensions that you may want to try out for yourself, and maybe you can study with your friend or something like that. If you are interested in a lot of this stuff, you can go to www.physicsbootcamp.org. If you like, you can subscribe to this channel and leave comments, suggestions if you want some problems to be addressed or something like that. I will see if I can solve some of the problems that you suggest. So talk to you later in another video. Bye.